Jay has just measured the length of a piece of wood to be 34.4 centimeters, plus or minus 1 centimeter. What does that number mean? Precision is the smallest degree of measurement that you can see in a measured number. The precision of Jay's measurement is 1 decimal place of a centimeter. Each place in a number has a name: hundreds, tens, ones, etc. Numbers that have more defined places to the right are more precise than those that don't. For example, the number 11.1 centimeters is precise to 1 decimal place. The number 11 is precise to the ones place. 11.1 centimeters is more precise than 11 centimeters. It contains a deeper level of information and a finer detail. Uncertainty is an indicator of how much confidence we have that we could repeat our measurement and get the same number. The precision and unit come from the instrument we're using, in this case a ruler. The numeric value and associated uncertainty are decided by the person who is using the instrument. For example, we use a thermometer to measure our body's temperature. We can see from the thermometer that the unit is in degrees Fahrenheit, and the smallest measurement or precision possible is 0.1 degrees Fahrenheit. Let's blow up this portion of the thermometer to see that more clearly. The measurement 97.6 degrees Fahrenheit represents any measurement that lands in the colored zone that marks the halfway points between 97.6 degrees Fahrenheit and 97.7 degrees Fahrenheit above, and 97.5 degrees Fahrenheit below. If the measurement had landed outside the colored zone up here, it would have rounded up to 97.7 degrees Fahrenheit. If the measurement had landed below the colored zone down here, it would have rounded down to 97.5 degrees Fahrenheit. The halfway point here is 97.55 degrees Fahrenheit. The halfway point here is 97.65 degrees Fahrenheit. So the number 97.6 degrees Fahrenheit really represents all the values from 97.55 degrees Fahrenheit up to, but not including, 97.65 degrees Fahrenheit, because 97.65 would round up to 97.7. Another way to state that is 97.6 degrees Fahrenheit plus or minus 0.05 degrees. If we think that our measurement was that good, truly in this zone, then we don't need to add that uncertainty. We just write 97.6 degrees Fahrenheit and we all know what it means. However, if the thermometer numbers were so small that we couldn't actually be sure we were reading the measurement correctly, or if the thermometer was moving around a bit and we got a different value if we looked at it a second time, we should add some extra uncertainty. For example, this image shows the thermometer with lots of tiny little lines, each separated by 0.1 degrees, too tight to easily read. Maybe the value is 97.6, but sometimes it looks as high as 97.8 or as low as 97.4. So we'll note that extra uncertainty in our final answer by writing 97.6 degrees Fahrenheit plus or minus 0.2 degrees Fahrenheit. In this case, the precision is 1 decimal place, and that's set by the instrument limits. The uncertainty is based on how well we can read the instrument, and that's plus or minus 0.2 degrees Fahrenheit. What happens when the tool we use to measure has a precision much greater than our uncertainty? For example, when we use Google Earth to measure a distance between 2 points, we get a precision of many decimal places, 9.443225 kilometers. But what if the 2 points that we're measuring the distance between are not very precisely located? When we take the measurement multiple times, we get multiple answers. There seems to be a fair bit of uncertainty, plus or minus 0.2 kilometers. Writing our answer as 9.443225 kilometers plus or minus 0.2 kilometers is kind of crazy, because while the instrument measurement is precise to 6 decimal places, the uncertainty is precise to only 1. And that lower precision makes all those extra decimal places in the measured number meaningless. The measurement could really be as high as 9.6 kilometers or as low as 9.2 kilometers. So we round our measurement precision to match our uncertainty precision, and the answer would be 9.4 kilometers plus or minus 0.2 kilometers. We can always round to make a number less precise, but we should never make it more precise. Now what happens when we perform a mathematical calculation with a measured number? For example, what if we add or multiply two measured numbers together or double a measured number? What do we do about the precision of the final result? The key here is to ensure that our final result is not implying a greater precision than we originally measured. That would be false information. Let's look at another example. John uses this ruler to measure a piece of wood. The precision limit of this ruler is 0.1 centimeters. His value for the wood is 34.4 centimeters, with an implied uncertainty of plus or minus 0.05 centimeters. He's added no extra. Julia uses a different ruler to measure a piece of wood that is the same size as John's. The precision limit of her ruler is 1 centimeter. She measures the length of the wood to be 34 centimeters, with an implied uncertainty of 0.5 centimeters. No more. John's value is more precise than Julia's. What do we do when we add their two lengths of wood together? What's 34.4 centimeters plus 34 centimeters? Just doing the math, we get 68.4 centimeters. But is it correct to maintain the precision of the most precise value in the sum? Or do we have to round to the least precise? Which one can we stand behind as being correct? The more precise or the least precise value? If we write 68.4 centimeters, it comes with an implied uncertainty of plus or minus 0.05 centimeters. But wait, Julia's piece is more uncertainty than that. Julia's uncertainty of plus or minus 0.5 centimeters is 10 times the uncertainty of John's. To have an answer of 68.4 centimeters implies more precision than is correct. Julia's piece has more uncertainty than that. So we round our answers to match the least precise measured number. That's important because a measured number loses its value if we can't trust its precision. If we round to the ones place, which is the precision of Julia's number, we end up with a final sum of 68 centimeters, which means it has a plus or minus 0.5 uncertainty and could be anything from 67.5 centimeters to 68.4 centimeters. And that is more reasonably true based on what we know of Julia's measurement. What do we do when we multiply two measured numbers together? We can't simply round the answer to match our starting precision. Let's see why not and what we do as a result. The area of a square that has 34.4 centimeters on one side and 34 centimeters on the other is 34.4 centimeters times 34 centimeters equals 1,169.6 square centimeters. Now let's look at the ranges of the two starting measurements. We know that 34.4 centimeters could be as high as 34.45. That's the uncertainty implied by that precision. And 34 centimeters could be as high as 34.5 centimeters. That's the uncertainty implied by that precision. So let's complete the same calculation with the highest range for each number and again with the lowest. Then we can compare these answers to see the range of results and calculate our uncertainty. This range of possible answers from 1,150.725 to 1,188.525 square centimeters are plus and minus about 19 or 20 square centimeters. The original answer, 1,169.6 square centimeters, is much more precise than our uncertainty, so we'll round it to the tens place to match. Final answer, 1,170 square centimeters, plus or minus 20 square centimeters. Every time you take a measurement, if you can't be absolutely sure that your measurement matches the instrument's precision, add some uncertainty. A good way to decide if you need to add more uncertainty is to ask yourself if someone else in the class taking the same measurement using the same tool would come up with the same answer. Would your answers overlap? If you aren't absolutely sure that you set your ruler in the right place or were able to line everything up perfectly, add a reasonable amount of uncertainty so that your measurement and any other student's measurements would overlap. How to do this? Try taking the measurement 3 times yourself and see what range of answers you get. If they're all identical, that's your number and you need no more uncertainty. If, however, you are getting slightly different answers, add the appropriate plus or minus uncertainty to the average of your measurements so you're sure that your final answer overlaps with all your measurements. Pause now. Pause now.